So one thing to note is that we are enumerating these sets. So one thing can go wrong is we start with a set, we proceed and come back with the same set again, right? So you need to show that same set will not repeat again. So let's say dk be the set D at the kth iteration, and we will prove that the dk will not repeat ever again. Once it's showed up in our set and as the algorithm proceed, dk will not come back again. How do we prove that? Okay. So let's suppose we assume the contrapositive. In lth iteration there was a D, and the same D appeared again at the kth iteration. Okay. And L is later iteration than the kth iteration. Between this L to k iteration, there's some iteration where the highest index, okay, which left D and come back. Okay. So what may have happened? Think about it. You had some set of vectors at kth iteration and the same set of vectors at the lth iteration. So some vectors must have left over time and they must have come back. So pick the vector which has the highest index that ever left in this process and came back. Okay? And the point where it left was P and came back is Q. You may be imagining that maybe P's R may be leaving multiple times and coming back. Don't worry about those situations. We just pick any P where it's leaving, any Q where it's returning back, and then theorem will work even if the R leaves again between Q and L and come back. That's all. It's okay. So one thing to notice is that in this process between P to Q, okay, so the important thing is the timeline between from pth iteration to the qth iteration. So all the vectors which are bigger than r plus 1, which are in the set dp and dq, will neither leave or not join, because this is ar is the largest one. Okay. So if you draw the line of indexes from 1 to m, so there are m vectors, remember that. So and then we have m indexes. So this rth is the position which we have which were with the highest one, which left and came back. At the pth iteration, this vector must be there, rth vector must be there, that so that it can leave. Okay, and at the qth iteration, this vector must not be there so that it can come back, right? And all the bigger vectors, okay, all the vectors with bigger indexes must be there. They neither leave, they neither join, they stay over the period of from p to q. And for lower ones, you don't have a guarantee. Okay, they can do whatever they want. Okay, so let's make an observation. So at the dp, okay, so rth vector is leaving, right? So let's break it down. You must have expressed b in terms of some linear combination, and you must have observed that the linear coefficient for everybody less than r must have been greater than or is equal to 0, otherwise they must have left. At r it must be less than 0. Okay, that's why you left the rth vector left. And these are two important facts, please remember that. Next thing to remember is at the qth iteration r is coming back. So that means is that cq, whatever the c you must have found at the qth iteration, and their b must have been less than 0. Okay, the dot product must have been less than 0. So you observe these following three facts. Okay, the first fact is why rth vector came back, because cq aj, okay, anything below r must have been greater than or equal to 0, right? Rth1 must have been -1, right? And everybody else which are in this set of D must be 0, because they are sitting on the hyperspace defined by the vector C. Here's the pictorial way of defining these facts. So here I am saying is that all these guys below R is greater than or equal to 0. And at rth position you have less than 0. Right? Now we observe that in the case of the red qth iteration, you have CQAG greater than or equal to 0, everything below the R. Okay? At this position, what will happen? That you have a less than 0. Okay? And for greater than R position, you have 0. So see that qth and rth iteration both will match at this point. They will be exactly same set of vectors, and then CQAI QJ is equal to 0. Yeah, please remember this picture. Now using this picture, I am going to derive contradiction. Amazing, right? So here's a picture copied again, and what do? I say CQB. Okay, CQB. What is CQB? CQB had to be less than 0. Now I'm going to prove it that it may be non-negative, and if I can prove it's non-negative, then it's a contradiction and you have proven determination. So let's break down B. Remember, the B was written in terms of these guys. Okay, so now I'm going to write that again. So B is written as a linear combination of those vectors that occur at pth iteration. Now I expand, I will push CQ inside, so then I will find that this vector CQB is a sum of these terms, and also each of these terms is non-negative. How do I do that? Well, look at this. This is greater than or equal to 0 multiplied by greater than or equal to 0, it gives you non-negative. At this point, they are less than 0 and less than 0. Okay, they multiply them, they give you non-negative. At this point, one guy is always 0, right? So they will give you non-negative output. Therefore, their sum will be non-negative. And you are done with the proof. One important thing to note is that this proof does not say that if a vector leaves, it cannot come back. It can come back. When it does, somebody else at the higher index needs to leave. Okay? Otherwise, it cannot come back. And this property is being used to derive the contradiction.